So there are various avatharams of Cauchy's theorem, some of which we have already seen. So now let's discuss something like a general form of Cauchy's theorem and corresponding Cauchy's integral formula. Now, if you look at all the forms of Cauchy's theorem that we have seen so far, everywhere you'll see a term like following. For example, for a Cauchy's theorem for a triangle, so what is that? So if you have a triangle in the region whose interior is also contained in the region, the domain, then, or even for a convex set or a star-like set, you have a contour, closed contour, which is in the domain, together with its interior, so on. So everywhere the closed curve and the interior must lie in the domain, right? So this is true in general. That is, the general form of Cauchy's theorem can be stated as, if you have a domain omega and a function which is analytic in omega, then integral of fz dz over C, any contour, with the same condition, which lies along with its interior in the omega, it is 0. So everywhere this condition, the interior also should lie in the domain, comes out. What is this condition? How is it expressed mathematically? In Cauchy theory. So, here is where what is called the index comes into the picture. Index of a curve with respect to a point, whatever. So remember, or if you want to put a 1 over 2 pi here, when say C is the circle, of course R you can write, doesn't matter, some circle around A with radius 1. Radius doesn't matter actually. Of course, we calculated this and saw that. Suppose you take as before, so this was your C. Suppose you call it C1 or call it C1 and call this as C2. If you integrate over C2, what do you get? And do the same thing as we did earlier, but what will we get now? You have an extra factor of 2, right? So when you differentiate, the substitute minus a is e power 2 power it, dz is 2t e power it, and so on and so forth. So you see that this is equal to what? Tell me, calculate and tell me. But what is the curve? What do you get? It's again the circle, the same circle, but what happens now? As t varies from 0 to 2 pi, it goes around the circle once. But here, 0 to pi, one circle again. So it goes around the circle twice. Right? Or, for example, if you take e power minus it there, it will go around the circle, but in the opposite sense. Right? So in that case, you will get minus 1, the integral as. So this integral there, this integral here, measures the number of times you go around the contour. Right? Or, as you say, number of times the point winds around the point center, let us say, the origin here. Okay? So that's why this is called the winding number, index or the winding number. Okay? So by definition, so NCA, let us say, is where C is any closed contour. Only thing you want is A is not on C, does not pass through C. This is called the index of C with respect to A or around A. Or the winding number winding number of C around A. Of course, first of all, you have to show basic property is that this integral is always an integer, positive or negative, or 0. So the basic property of this is by the way, so if C is a contour in a domain omega, okay, no, not this way, let's not write this way. So if you take a closed contour, okay, so if your contour is just like this, what about the complement? Consists of the interior and the exterior. There are two connected components. But your contour can be more complicated, right? The simple closed simple contour, what is called a Jordan, closed Jordan curve. Your contour can be like this, right? In which case, this is complement consists of this, this, and the rest. So if you take the complement of the curve, the plane, it can have more than two connected components, right? It will have just two connected components in the case when C is what is called a simple closed curve. It doesn't intersect itself. Because we are taking a closed contour, only one of these components will be unbounded. All other components, connected components, will be bounded. So this is one bounded component, this is one another unbounded component. I mean, this one bounded component, the other one is the unbounded component. There is going to be only unbounded component, and there may be one or more bounded components. So in each of these bounded components and the unbounded component is a constant on the complement of C minus C doesn't look good, so I'll write the complement of C. And moreover, the value in the unbounded component is 0. Some result in topology are easy to state, but not so easy to prove. The Jordan curve theorem is one such. If you take a simple closed curve in the plane, the complement of the curve has exactly two connected components. One of them is bounded, the other unbounded. The bounded component is called the interior, and the unbounded component is called the exterior. This is the content of the Jordan curve theorem. Although intuitively it is obvious, but the proof is rather difficult. So now you go back to the condition that you usually write in Cauchy's theorem. The closed contour and the interior of the contour both lie in the domain, which means what? In terms of these winding numbers. But in this case, for example, this part and this part also lie in the domain of definition of the function, right? So how do you express the condition in terms of the index? The index of any point outside the domain is 0. That is n. So suppose you have a C, you have a domain omega, and C is something inside omega. Saying that the interior of C, suppose we have not properly defined what is meant by interior of T, right? It doesn't matter. So the interior C also lies in omega, can be expressed by saying that index of C for any point outside the domain is 0, right? So that is so this gives what is called the homology version of Cauchy's theorem. Don't worry about the term right now. I'll say something about it a little later. Okay, so what is the general form of Cauchy's theorem? Integral over C f z dz equal to 0 for any C for which NCA equal to 0 for every A in the complement of omega. Okay? So there is a term that is usually used. If this condition is satisfied, you say that the closed contour C is homologous to 0 or null homologous. C is said to be course, everything with respect to the domain omega, right? So the general form of Cauchy's theorem can be stated using this terminology, or what is called the homology version of Cauchy's theorem. Alphos call this the most general and complete form of Cauchy's theorem, or something like that. There is also what is called the homotopy version of Cauchy's theorem. But homotopy is a stronger condition than this homology condition. So omega is a connected domain, open connected set. C is a closed contour. In omega, which is null homologous. Then for all analytic functions, all f analytic in omega. The proof of this is not so easy. Even in the I haven't brought the book. So even in the second edition of Alphos, there was a proof given by Bearden, which supposed simpler than the proof given in his first edition. I think that's what is given in third edition also, what you are looking at. The third edition itself, I think, came out in 1966 or something. But in 1971, a much simpler proof has been given. So in some of the modern books, you can find that proof. So later, proof due to Dixon. It's fairly simple. Surprisingly, it uses Lewis theorem. Okay, so I'll try to briefly indicate the proof, okay, without going into the details of the proof. And then make some general noises. Okay, actually, then I'll add a statement there. Then, before writing this, I will write the Cauchy integral formula in this setting. And this will be a consequence of that. the Cauchy integral formula. And then the usual Cauchy's theorem. For all f analytic in omega, we have these two statements. We'll indicate the proof of 1, and 2 is almost immediate from 1. So define everything in the domain. I will not write all that. The essential trick is to view this as a function of two variables. Then integrate over C with respect to one of the variables. Then observe that it is a function, analytic function of the other variable. G is analytic this is actually quite simple. Use Morira's theorem. You integrate this over a triangle and change the order of integration. That's it. As I said, I will be just writing the various steps involved, right, without going to the details. Okay. But this is quite simple step. Look at all points where you have that condition homologous to 0. All points Z and C. Using H because homology comes in. So what is the assumption? C is homologous to 0. So essentially it means that the interior of C lies in omega itself. And of course, outside this we know that the index is 0, right, in the unbounded portion. So you have that omega union H is the whole of C by assumption. You can also easily verify this. This takes less than a minute to verify. For all Z in the common portion, Gz which we have written. Okay, anyway, so C, integral over C. So each thing that I'm writing will not be obvious, right? You'll need to do a little work. So now we can therefore define a function on the union, which is the whole of C. So on omega, you define it, you have already defined like this. On H, you define it like this. Okay? And on the intersection, you have this already. So on the overlap, the definition match. So G is that way defined on the whole of the plane. Therefore, if we define G on C by, so Gz is this on omega and Jz is this on H, G is well defined, okay, on whole of G, whole of C. See, like you are having two functions, one on A, another on B. Suppose the two functions agree on A intersection B, then you can define a function on the union, right? That's what we are doing. So this is a function on H, this is a function on omega. On the common part, they agree, therefore gives you a function on the union. Okay? G is analytic on C. G goes to 0 at infinity. You can see, I mean, mod z goes to infinity, this integral itself goes to 0, right? Z is in the denominator. So it's not difficult to show that Gz goes to 0 at infinity. So you have an entire function vanishing at infinity. Any continuous function which vanishes at infinity is bounded, right? Vanishes at infinity means small after some stage, but by continuity bounded inside the bounded region, right? Like compaction. So overall it is bounded. So therefore is a constant by Lewis theorem. But what is a constant? G goes to 0 at infinity. So you can't have a non-zero constant going to 0 at infinity, right? So this constant must be 0 because of this. A non-zero constant doesn't go to 0 at infinity, okay? If G is equal to 1, identically, limit at infinity is 1 or not 0, okay? So what does this mean? Integral of this, what you have there. G is integral of this. H is this. So integral f z, split that into two parts. This divided by this minus this divided by this. F z times the index. Right? That's how the index was defined as 1 over 2 pi I times the integral of dz over 1 minus z. If you take this out, dz yz minus zeta. So there is the index of it. So that gives you this 1 over 2 pi I equal to f zeta times the index. Right? That's what you have here. Apply 1 to the function phi z this is again an analytic function, right? In place of f, you take z minus zeta times f. So what happens to the integral now? You write h here. So you're going to just have integral fz. Okay? Replace fz by z minus zeta times fz. So you are going to, on the right hand side, you are going to get the integral of fz over c. Multiply by 1 over 2 pi, never mind that. But what happens to the left hand side? H of zeta. Right? I mean, phi of zeta. Phi of zeta is 0. Right? So the left hand side is 0. So 0 equal to 1 over 2 pi I integral c f z dz. I can forget the 2 pi I because it is 0 on the other side. So that gives Cauchy's theorem. So it's a pretty simple proof. See, none of the steps that I have mentioned is difficult, right? Each requires a little work, but none of them is difficult. Some of them are more or less obvious. Some of them need a little work. So all that you need for the Cauchy theorem to hold is that the curve should be, the contour should be homologous to 0. That's all. Right? So this is again a topological concept. By the way, the concept of winding number or index props up in various places. So arises in many places in topology, geometry, and even analysis, functional analysis even. There is a little book published by the American Mathematical Society by John Rowe, called Winding Numbers in Topology, Analysis, and Geometry. So contains lots of very nice things involving winding numbers and other things. AM has a series called Student Mathematical Library or something of that kind. That series you have. For example, in topology, for example, it can use to prove the what is called the no retraction theorem. or equivalently the Brouwer fixed point theorem. If you take the unit disk, mod z less than or equal to 1, a closed unit disk, there is no continuous mapping of the unit disk to itself which maps the boundary to the boundary, which fixes the boundary. Right? F from the closed disk to closed disk such that f z equal to z on the boundary, identity on the boundary, all leaving all points on the boundary fixed. There is no such continuous map. This is what is called no retraction theorem. So this, if there is a map like that, you say that the boundary is a retract of the closed disk. So that's why it's called a no retraction theorem. So, and then this is, you can derive the Brouwer fixed point theorem for the disk from this, which says that any continuous map from the closed disk to itself has a fixed point. Okay. Just like any continuous map from a closed interval to itself has a fixed point. That's the easy consequence of the intermediate value theorem. Okay. So this is true in any dimension. In dimension 2, you can use winding numbers to prove this. Of course, this is true in higher dimensions also, but the proofs are more technical. Okay, so homotopy is a very important concept in all of mathematics. Okay, one more thing I want to say, because people are doing functional analysis somewhere. So, and functional analysis, there are what are called Fredholm operators. So there is what is called index of Fredholm operators and so on. So in Fredholm theory, again, this is useful, the concept of winding numbers. Homotopy also, actually. Homotopy, of course, props up in all kinds of places. So what is homotopy? In simple terms, it's continuous deformation. You understand the term? Deformation, deform, or deformation. So you say that two curves are homotopic if one of them can be continuously deformed to the other. So what is the meaning of this? You have a curve like that, you have a curve like this. Starting with this, you can just move this continuously so that you end up with this. Like that. Of course, for our purposes, we are interested in closed curves. So we don't want to, so we want to look at closed curves at a point, all based at the same point. So if you can continuously move the other one without moving the base point, let's say. Right? All of them are loops at some point, z0. So two loops at z0 are loop homotopic if you can move one loop to the other in a continuous fashion. How do you put it mathematically? You have a continuous family of curves, right? Starting with one and ending with the other. So in other words, there are two parameters involved now. One for each curve and another for going from one curve to the next curve. There is no next, but other curves. Okay, so it's a function of two variables. So, or 2 points in the plane. C1 and C2 are two curves joining Z0 and Z1. I will change notation. I will call this gamma 1 or alpha 1, alpha 2. Alpha beta, maybe. In C, of course, definitions are all valid in any topological space, but we are interested only in C now. So what do you mean by curve? From a closed interval, we can always take it to be 0, 1, continuous, such that alpha 0, initial point Z0 and end point Z1. So these are alpha beta are path homotopic. The only difference is that the endpoints are always fixed, right? You have a family of paths like that. You have a continuous family of paths if there exists a continuous map H So as I said, one interval is for each curve, parameterizing each curve, and the other interval is for parameterizing the family of curves. H of S0 is alpha S. So at t equal to 0, you get alpha H of S1 is beta S. So you start with t equal to 0 at alpha and end up at beta when t equal to 1. But the endpoints all fixed always. That means H of 0t is always Z0. H of 1t is Z1 for all t. In other words, if you for a fixed t, if you write alpha t of S is H of St, so alpha t is a curve, right? With initial point Z0 and end point Z1. So you have a family of curves alpha t as t varies from 0 to 1, starting with alpha, right? Alpha 0 is alpha, and t equal to 0 you have alpha, and t equal to 1 you get beta. So you have a family of curves alpha t starting with alpha and ending with beta. So each alpha t is a path joining Z0 and Z1. So I have a continuous family of paths joining Z0 and C1, starting with alpha and ending with beta. That's all it does, right? This homotopy, I just call a homotopy or path homotopy from alpha to beta. So in particular, of course, we are interested in loops, which means the end point is the same as the initial point for us, right? So if Z0 equal to Z1, we get loops at Z1. Or closed paths, we call it loops. So there are a couple of observations now before I get back to more about this path homotopy. If you have two closed curves, and you have a domain and all that, right, which are path homotopic or loop homotopic. We have two loops like this, let's say, which are homotopic, then many things happen. One, index with respect to index of one curve is same as the index of the other curve. Number two, for any analytic function, integral over the first curve of f z dz is same as the integral over the second curve. So in other words, homotopy winding number or index is a homotopy invariant. And so is the contour integral along a curve. Okay, I have written that anyway. So winding number and integral are homotopy invariant. By which is meant that if two curves are homotopic, loop homotopic, then the index of the two are the same with respect to any point. Number two, for any analytic function, integral, so all this, what it means is n C1a is equal to n C2a for all a, and integral C1 fz dz is same as integral C2 fz dz for any analytic function f. So in particular, when you consider loops, the constant loop. What do you mean by constant loop? A constant function. What is a loop? The function from, say, 0, 1 to c, so that alpha 0 is equal to alpha 1. Right? Suppose alpha is a constant equal to z0. This is what is called a constant loop at z0. There is no loop, just a point. Right? So suppose you consider a constant loop. What happens to the integral? Integral over a point. 0. Right? So, in particular, what does this give you? If you have a contour which is homotopic to a constant loop, then integral along C is 0. Okay? If C is homotopic to loop homotopic to a constant. So you can state it more elaborately as that if you have a function which is analytic in a domain omega, and C is a loop in omega which is homotopic to a constant loop in omega, then integral f is 0. So this is the Cauchy, the homotopy version of Cauchy's theorem, right? Now, there are domains in which all closed curves are homotopy to constants, like the disk or the whole plane, right? The easiest way to see that, of course, geometrically it's fine, but you can just write down the straight line homotopy. If you have even two paths, you don't have to consider even loops, right? If you have two paths like this, both of them can be loops, that doesn't matter. So how do you go from one to the other? Just join the corresponding points by straight line segments, right? So one is alpha t, another is beta t. Look at the line segment joining alpha t and beta t. That gives the homotopy. So you can deform, just push this point along this line segment to the other point for each of them, right? On the other hand, there are domains where this is not possible. If you take an annulus, for example, if you take a circle like this, you can't deform to a point. Homotopic to a constant means what? You can shrink the whole circle to a point. Okay? But you can't do that for the circle. You have to do it in the domain, within the domain, right? Of course, you can do it in the whole plane for everything, right? But lying within the domain, all the intermediate curves should lie in the domain. So that you can't do, right? You can go on shrinking the circle, but you can go up to only the inner circle there. You can't go beyond that. There is an obstruction there, right? But whereas even in the annulus, if you take a circle like this, then that can be shrunk to a point. So in general, this may or may not be possible always, shrinking a closed contour to a single point. If we can do that for every closed curve in the domain, or restating that, if in a domain omega, every closed contour is loop homotopic to a constant, then you say that the domain is simply connected. Simply connected. So the connected domain omega. Every loop in omega is null homotopy. Null homotopic means homotopic to a constant. So, in such a domain, integral fz over c is always 0 for any analytic function f and any closed contour c, right? So, in such a domain, is true for all c and for all f, meaning for all closed contour c and for all analytic functions f. And well, null homotopic implies null homologous. So the homology version of Cauchy's theorem is stronger than the homotopy version of Cauchy's theorem. Right? That homology version says if C is homologous to 0, then integral is 0. Right? So, but if C is homotopic to 0, then it is homologous to 0 and therefore integral is 0. So, this actually follows from that and this to that. That's why alpha calls the homology version the final and most complete version of Cauchy's theorem. Okay, so it's past time. So let me make a few noises, general noises, before I conclude about this homotopy and all that. So you start with a domain, okay, and define a relation by fix a point z0, look at all loops at z0, okay. So say that a loop alpha is related to a loop beta if alpha is loop homotopic to beta, okay. So this is easily verified to be an equivalence relation, okay. So the equivalence classes are called the homotopy classes, loop homotopy classes. How do you combine two paths, two loops for our purposes? If you have one loop and more loop, go through the first loop and then go through the next loop, right? So that gives a product of loops. You can actually define maps alpha star beta of t, alpha to t minus 1, you can check that this is a more generally if alpha starts from z0 and ends at z1 and beta starts at z1 and ends at z2, then alpha star beta will start at z0 and end at z2. Z0 to z1 via alpha and z1 to z2 via beta. But in particular for loops, it goes around alpha and then goes around beta again. That's what this does. So this gives a product of paths, product of loops. And this equivalence relation respects these products. That means if alpha is homotopic to alpha 1, beta is homotopic to alpha beta 1, then alpha star beta is homotopic to alpha star what? Alpha 1 is homotopic to beta star beta 1 and so on. So in other words, you can define a product for loops by defining equivalence class of alpha and equivalence class beta. You can define as equivalence class of. So this is well defined and satisfies the associative property. The constant loop at Z0 acts as the identity. In other words, alpha star, the constant loop, is homotopic to alpha itself. And once you have a loop, you have what is called the reverse loop. The same loop traversed in the opposite orientation. So that gives the inverse. The equivalence class of that gives you the inverse of this, and the set of all these loop homotopic classes form a group under this multiplication. So this is what is called the pi 1 of whatever your domain omega is called the fundamental group. So these are all objects of study in algebraic topology. The first thing that you study in algebraic topology is homotopy and fundamental groups. And what does simply connected mean? Any two loops are homotopic there. So there is only one homotopic class. So everything is homotopic to the constant. So this reduces to a single point, 1 point group in that case. So fundamental group is trivial. Simply connected is equivalent to saying that the fundamental group is an one element group. Okay? Because we mentioned homology, let me also mention as related to this, its relation to this homotopy fundamental group. There is also what is called the first homology group. This is the first, the fundamental group is what is called the first homotopy group. There is a pi n for every n, the higher homotopy groups. We will not talk about that. There is also what are called the homology groups. So H1 of omega. So this is the first homology group of omega. I am not going to say anything about that, even roughly. Okay. The essential difference is that the fundamental groups are in general non-abelian. The homology groups are always abelian. And H1 is got from pi 1 by what you call as abelianization. If you start with a group G, you look at the commutator subgroup. You know what the commutator subgroup is? You look at all elements of the form A, B, A inverse, B inverse. Look at the subgroup generated by all such elements. This is called the commutator subgroup, and generally denoted like this. The normal subgroup, you can form the quotient group. This becomes an abelian group. And in fact, this is the smallest subgroup which makes the quotient abelian. So when you do this for the fundamental group, you end up with the homology, first homology group. That's why you get all this. For example, why homotopically trivial implies homologically trivial, right? If the fundamental group is trivial, then this is also going to be trivial, right? Because that's a quotient group of that. So homotopically null implies homologically null because of this. Homology is a quotient of homotopy. So anyway, so this is all a lot of topology behind all these general versions of Cauchy's theorem. All this go through in general topological space as well, but here in the complex domain, usually the definition of simple connectivity without going to homotopy can be given as a domain omega is simply connected if the complement of the domain in the extended plane is connected. Not in the plane itself, but in the extended complex plane is connected. That is equivalent to this general topological version of the definition. So, I mean, some books give this definition, or some books give other definition, and so on, I suppose. Alphos probably gives the definition, the complement in the extended plane is connected, and probably Conway gives the homotopy definition. Probably. I don't know, something of that kind. So all this homotopy and homology and all that go back to Poincaré. You come across this name? When? So is Poincaré's Poincaré, okay? O-I is wa sound, Poincaré. So his first paper on what was then called analysis situs, what we call topology now, appeared in 1895. The homotopy and fundamental groups and homology were all defined in that paper. Poincaré is so to say, the father of algebraic topology, of many other things. Okay. One of the most profound and wide-ranging genius. Incidentally, he came to develop algebraic topology in his study of what is called celestial mechanics. That means the three-body problem, the motion, the relative motion of the Earth, Moon, and the Sun. So it involves differential equations, and the differential equations involved are not easy to solve, and so on. So he was studying that problem of three-body motion. So he came up with that paper. All right, so according to Alphos, the homology version of Cauchy's theorem is due to Emil Artin. Who was a student of Hilbert, basically an algebraist, but he had profound influence on many areas of mathematics, in the development of many areas in the 20th century. Yeah. So he was a student of Hilbert at Göttingen. So the homology version, according to Alphos, is due to Artin. So there are, of course, lots of other things which I have not mentioned at all, for obvious reasons. In fact, I was hoping to say something about simply connected domains, lots of equivalent formulations of simply connected domains. For example, you can define, if you have a function, analytic function which does not vanish at all in a simply connected domain, it has a logarithm. That means there is a function g analytic on omega, so that e power g is f. This you can do only in a simply connected domain. So there are lots of other nice things like that. Okay, so everything has to come to a close anyway, so let's close here.